So now we come to our last and final method for doing indefinite integrals, called partial fraction decomposition. And unlike the previous two methods that we looked at, change of variables and integration by parts, partial fraction decomposition is much more limited in scope. It can only be used to integrate rational functions. That is to say, the integrand is going to be expressed as the ratio of two polynomials. And the basic idea is that we're going to re-express that rational function in terms of its partial fraction decomposition, and then we're going to integrate that because it'll be simpler and easier to work with. Which means, of course, first we have to do partial fraction decomposition. So first we have to make sure that the degree of the numerator is less than the degree of the denominator, otherwise we have to do polynomial division. And we also have to suppose that the denominator is going to factor. Otherwise, there's nothing to do partial fraction decomposition with. And then once we get to partial fraction decomposition, we simply integrate each term. Let's see how this works with an example. So suppose I want to integrate 5x minus 3 divided by x squared minus 2x minus 3. I notice that both conditions are satisfied for doing partial fraction decomposition. That is to say, the degree of the polynomial's numerator, the degree of the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, and also the polynomial and the denominator factors. Okay. Now, it's worthwhile whenever we have a situation like this to see if we could do use substitution. In other words, if the numerator was a derivative of the denominator, I could do change of variables. But we see that it's not. So then we use partial fraction decomposition. So we go ahead and we factor the denominator, and we go ahead and set up the partial fraction decomposition. And we can do the cover-up method. You can do this a number of different ways. The easiest way is to do the cover-up method, where you basically take one of the factors, say x plus 1, multiply through by it, and you see what's going to happen when you let x be equal to negative 1. The term with b will go to 0, and then you just get a is equal to, and the left-hand side will be 5x minus 3 over x minus 3, just substitute in minus 1, and you'll get a is equal to 2. Okay. Or you could also set up a system of linear equations. Either one's fine. But if you're not familiar with the Heaviside or lookup method, you might want to check that out. So I get a is equal to 2, b is equal to 3, and so I have this partial fraction decomposition, and I can do each of these integrals now. On the right-hand side, I can do a use substitution, let u be equal to x plus 1, du is equal to dx, and I know now this integral will just be the integral of 2 over du over u. And the same thing here, I can let u be equal to x minus 3, du will be equal to dx, and the same token I'll have plus 5 du over u. And you integrate both of these, and your final answer will be 2 times natural log of x plus 1 plus 5 times natural log of x minus 3 plus my constant of integration. Okay? Let me show you a second example that's a little different. Suppose, for example, we want to integrate the quantity 3x minus 2 divided by the quantity x cubed minus x squared plus x minus 1. Well, the degree of the polynomial in the numerator is less than the denominator. That's good. The denominator factors, but we notice that one of the factors is what we call irreducible. Okay, this factor does not reduce down. It cannot be expressed as a product of linear factors in the reals. So when we have an irreducible factor, we remember that we always need a polynomial of 1 degree less than the irreducible polynomial. And anyhow, I set up the system of equations and I go ahead and solve it, and I'll let you do this as an exercise, but you'll find out in the end that when I go ahead and basically cross multiply to put everything under a common, basically when I put everything over a common denominator on the right hand side, I get this equation right here. I'm going to equate coefficients of like terms. So I see that a plus c has to be 0. So a has to be minus c. And then I focus on the last two terms, which tells me b minus a has to be b minus a, which is now b plus c, is equal to 3. That's the x to the first term. And c minus b, which is the constant term, has to be minus 2. And you can solve these, and you get the following result for the partial fraction decomposition. And you notice that in the first term, where the denominator is x squared plus 1, the numerator is not the derivative of the denominator. So I have to break this up actually into two terms, x over x squared plus 1, and another term which is just 1 over x squared plus 1. And I can integrate those each separately. Whoops. Hold on. Okay, and so I'm going to end up integrating those. The first term, of course, I can do u substitution. U is equal to x squared plus 1. The second integral we recognize as being the arctangent. Okay, and the third term, again, I can use substitution, and this will be my final answer. Okay, all right. Hopefully that does it for partial fraction decomposition, and again, I'll give you some problems to practice on.